Let's record. Okay. All right. Looks like that's showing up okay. All right. Hello, everybody. If you do not know me, I don't think I've ever seen most of you before, so chances are I'm probably a new face as well. My name is Nathan Jessurun. I'm a graduate student, fourth year PhD student, so I'm like 6 months away from actually getting my degree, so I can see the light. But I'm working at the Florida Institute for Cybersecurity Research. The FIX Lab is what it's commonly known as around campus. My advisor is Dr. Naveed Asadi, if you've heard of him or seen him or read any of the papers or anything. And if you have questions about what it would look like to either accept an OPS student position there, so working for pay, or if you wanted to start a grad position there, either as a master's or a PhD student, I have lots of information I could give you. And if that's an avenue that you're interested in pursuing, let me know. And it might be more relevant if you see the actual information that's being presented, if anything that like that looks interesting to you. Yeah, I'm happy to talk about it further. But as far as details about me, a little bit more, let's see if working. There we go. Yeah, so I graduated in 2019 from Cedarville University, which is a small school near Ohio State University with a degree in computer engineering, and took some digital logic courses, really liked those. Went on a preview tour of the University of Florida during February, the dead of winter in Ohio, and the weather was phenomenal. The stipend was decent, and so I was like, yeah, I'll start a PhD school here, or I'll start a PhD at the FIX Lab. And so that's how this kind of started. And since then, I've been doing a lot of research on hardware assurance and cybersecurity. So my specific portion is more about taking pictures of devices with digital cameras, so something pretty straightforward, and looking at those pictures to see if there's anything suspicious about them. So if somebody has swapped out one of the integrated circuits on a printed circuit board with something else, how would you figure out whether what you had in front of you was genuine or not? So one common example is like if you buy a router from Walmart and like the packaging might be a little bit damaged, how do you know that it wasn't someone who swapped out one of the components and put it back on the shelf so that they can wire all of your network traffic through their own backdoor or something like that? And it's a tricky problem, but we're looking into solutions that basically take less time than manual inspection of everything. And that's the motivation for a lot of what I'm doing. And you'll see that on one of the slides. But just as a quick overview of other things that can happen. So I mentioned the Walmart interception of a router on the shelf. But another thing that people commonly do, I don't know if you've heard of mod chips, specifically with regard to Xboxes, is it's where it broke the news. People who didn't want to pay for games, but wanted to play them anyway. It turns out there are some wires you could bridge together to short the intellectual property checks that Xboxes would do to make sure that the game was legitimate. And based on just bridging this gap between two pads, as you can see in that picture, you could play games that didn't have appropriate serial numbers to go with them. So if you bootlegged it, you could still play the game. Xbox tried to fix this in the 360 at least with saying, well, it'll be a lot harder for people to bridge the gaps between two pads on this board if we put it into one package, right? So add the IP validation logic on chip, and that way, if it's all uncovered in a silicon package, you can't just bridge the gaps. Well, very determined people figured out that if you drill a hole in just the right spot in that package, you can actually sever the bond wire between the logic that checks for the intellectual property logistics and the logic that says, yep, this is a good game to play. And if you sever that connection and enter a default error state for the board, basically you can still play these games anyway. So people who are very determined, especially gamers, I guess, ended up using those to do what's called an infield implant attack. And it's one thing to say, haha, I got to play a $60 game for free. The slightly more finger biting, or fingernail biting, I should say, aspect of this is when you order a computer online and the NSA says, what if you're going to do something suspicious with this computer? And so they intercept this in transit. Maybe during the shipping, you get a message that your package has been delayed or whatever. In reality, these people have taken your package off of the line or off of the delivery car or whatever, opened it up, put some device on it, and closed it back up and sent it on to you. So that's an example of interdiction. If you wanted to look up more about that, there's some interesting aspects of of how that happens with nation states. And that one's a little bit more, I guess, serious than just playing games, because there's a lot more security risks and a lot more information that can be compromised in something like this. So all of that to say, the idea of attacking these circuit boards is fairly serious, and something that industry and research, and especially the government too, wants to address. And that problem is made even worse. It's not just the fact that the individual board could be attacked, but there are many, many stages that go into how these boards actually go from the head of a designer in California to your desk on your computer. Part of that is, so they make the design files, they send those design files somewhere, somebody fabricates those boards, there's components that are sourced from somewhere else. So where do your integrated circuits come from? They're manufactured at a different place. Maybe a third company receives both the boards and the components and puts them together. Then they ship it to a fourth company that's responsible for distribution through a fifth or a sixth shipping channel before it gets back on shore and is sent your way. So because there's all of this outsourcing, and a lot of it is not really vetted for whether it's secure and whether it's reliable and whether they have good process standards, all of this is just making the problem more prolific at every stage. It's not just about assuring whether the final product you have is correct. Even the design could be modified, and it's difficult to know. And so this just presents us with some interesting challenges and opportunities for how to actually combat various aspects of this insecurity. So again, this is a real problem. What do we do about it? Well, the easiest solution is just to take a bunch of pictures, right? And I'm using the word picture very loosely. You can see several examples on the slide about what those pictures might look like. From the far left, that is an image of a integrated circuit with a terahertz TeraFlash Pro scientific MCube, whatever, there's a slide on it, you'll see. But it's a terahertz image, which is a little bit lower than infrared wavelength light. You can see through the package. And you can notice some of the structures on here, like bond wires. What's the die look like? What do the attachment points look like on the package? So those are underneath of the plastic packaging, but you can still see them because terahertz lets you do volumetric imaging. After that is photon emission spectroscopy is the image shown there. Digital camera. So if you just take a picture of a board and look for things like text, whether components are, or whether the pins on that package are broken or crooked, or whether they're all right, you can do all sorts of analysis with a picture, just a standard camera image. After that is way on the other side of the electron, or the photonic spectrum, which is X-ray, standard to like the same X-ray you would get in the hospital, except this one would kill you about 7 times if you tried to use it, because it's there's orders of magnitude more energy that's taken to image metal than to image people, because you still want the contrast. And then the other image there is a scanning electron microscope picture, where you can see the individual transistors and transistor logic that makes a chip work. And there's that pattern that you see in that far right image just repeats billions of times in any modern architecture. So I went over those really quickly, but they will be more covered in depth on future slides. But basically, as an overview, all of these techniques that I've talked about work on the electromagnetic spectrum, with exception of the scanning electron microscope, which I'll get into later. But this little box that I'm showing here is, yeah, I guess the one that's right here is the equipment that the Fix Lab has that can actually take pictures of various pieces of this electromagnetic spectrum. So if you're not familiar, like the same picture, like an X-ray of your arm or your your organs or whatever that you would get at a hospital, it's the same electromagnetic spectrum that you can see with your eyes. It's just a matter of whether the thing that you're taking pictures with is sensitive to that portion of the spectrum or not. So our eyes are sensitive to visible light, and the X-ray scanner or detector that you'd use at a hospital is sensitive to X-ray light. The other notable difference is the sun produces a lot of visible light. Not a lot of X-ray light gets through the atmosphere. So we have to produce our own X-ray source in contrast to being able to take pictures outside with a passive light source. So I don't know what happened there, but I don't think I did anything. Oh, there we go. Yeah, so it also says that my speaker's not working properly. Is there a way to verify whether this is testing? It looks like it's working. All right. It's fine. Testing 1, 2, 3.
Yeah.
No, oh well. I'll just assume that it's working and keep going, I guess.
Yeah, I think immediately it's good because that is like.
That's what I would assume. I just saw the pop up.
Yeah.
Yeah. Cool. So yeah. in any case, my goal for today is just basically to go very briefly through the different pieces of the spectrum that we can take pictures in, show you why that matters. And then I have some slides about grad school, which are complete. There's no segue there. It just kind of happens. But Cole, who asked me to come over here, said that some of you might be interested in learning a bit about like just very brief tidbit of like my 2 cents on grad school, so to speak. But yeah, going into the electromagnetic spectrum aspect of this. At the very, very low end of imaging. So if you think of red light is the lowest wavelength of light that we can see pretty much. And then below that is infrared, and below that is terahertz. So this is almost at like, if you think of 5G, the term that's been making the rounds is like terahertz energy is going to microwave your brain or whatever they say. This is a little bit higher than that 5G terahertz, but it's the same concept. So a little bit higher than radio waves is the low terahertz. And we have this box in the lab that you can see here, this TerraFlash Pro, which lets you actually send pulses into a sample and measure the signal that comes back. So you will take a probe and you'll take a picture of 1 pixel through the device. And the way that that works is you'll send a pulse, like again, at that 1 pixel and listen for the response. And you'll get reflections from different places in that sample. So if I took a single pulse on a chip, maybe like right over here, and if you're looking at the cross section, maybe that'll happen over here on the device, you'll get a strong reflection from the surface of the package. And then a little bit later, you'll get another reflection from the die right here. And then a little bit later, you'll get a reflection from the back side of the package. So you'll see 3 peaks that correspond to places in the package where you got a reflection. Hopefully that makes sense. The image that you see on the bottom is an X-ray. So this is not with terahertz, but it's just to verify that the information we're seeing is kind of correct. But the goal is if I can correlate, I know how quickly my pulse is moving, and I know what time I received that pulse. And if I put those 2 pieces together, I can get the exact thickness of different pieces of this device. And I can take cross sections of this pulse across the entire like array of pixels that I've imaged and get something like the image on the right here, which as you can see is you have structures like the die that's in the middle, you have the bond wires that are coming out here, and you have the pins that are on the sides. And you can use this to see, hey, is this some really cheap Chinese package that has just the picture or just the plastic on the outside, but there's actually no logic on the inside. You can see things like that pretty quickly with a terahertz device. The other nice thing about this is you can see things about the material that the device is made of. So if I took a picture with my digital camera, I mean, you can see if something is see-through or if it's not, but you can't really see what percentage silicon, like what material composition of silicon this package is. That type of information is not really visible in visible light, but it is in terahertz light. So you can actually see a little bit about like what are the constituent materials from this package, and you can use that the same way. Was this manufactured in a facility that has the right material that's making it? So that's some pretty interesting things that you can do with terahertz. We just got the machine a little bit late last year, so we're still looking into it, and there's some cool findings that are going to come out shortly. So a little bit higher than terahertz is infrared. So I think this one is a little bit more familiar to a lot of people. There's an infrared sensor in an iPhone that when you're doing face unlock or taking pictures in low light imaging, the infrared sensor will either boost the quality of it, and it can also increase the capabilities of facial detection and facial recognition for something like that. So that's where a lot of people might have heard from infrared. The machine that you see here is like beefed up on steroids several times. It's the machine is called PHEMOS. It stands for photon emission spectroscopy machine. And it takes pictures like you see in the middle here. And what's cool about this is what you're seeing is little flashes of infrared light across a space like you see here. And the brighter that flash is, the more rapidly something is switching. That something is a transistor. So you can literally see transistor activity in this picture. And the way that works is when a transistor switches from off to on, or from on to off, it emits a little bit of infrared radiation. And if these transistors are switching at gigahertz speeds, you can time your camera to take pictures at the same time. So this is also using an oscilloscope to get very, very precise measurements. But if you take pictures, the exact same frequency of these transistors are switching, and you average that over a long time, you get really bright spots of consistent frequency information for how quickly transistors are switching. So just a very brief pop quiz. If transistors emit infrared radiation when they switch, and more switching is what happens, like the more that something is switching at that frequency, the brighter of a spot you get. For those of you who have taken digital logic or something like it, what do you think this cluster of spots would be? It doesn't show up too well in this picture that I have, but you have a really bright spot and then progressively dimmer spots around it that are all very tightly clustered together. That's exactly right. So this is indeed a clock divider. Excellent. So, and you can use something like this to figure out where you are in reference to the design that someone has used. So like, because there's only so many clock dividers that are on a device, and clock dividers are specifically put where you need access to many of these separate frequencies. And so you can use these as landmarkers when you're doing statistical analyses, and when you want to compare where you are on the reference design. So that's something pretty cool that, like for me anyway, that matched the theory of how bit logic works and seeing some of these side channel analysis, which is what's happening here, just measuring some of the radiation that comes from them in the real world that's past logic alone. So I think that's kind of cool. But the question is, what do you do with this, right? So it's one thing to take pictures of the switching, but at a very high level, something that you can do with this is find out where someone's password is stored in secure memory. Or this specific paper is about finding where AES keys are stored in memory of a chip that's supposed to do secure encryption. But the analogy still works the same. So the idea is, if I was to enter my password on my computer so that it can let me in or not let me in based on whether I typed it correctly, how would it know to do that? It would have to take in my input, and it would have to know what to compare it against. How does it know what to compare my input to? Probably my real password is stored somewhere in memory that's very special. Like, it's not just stored anywhere in memory, otherwise anyone could read it. It's stored in a different place, but it still has to be fetched and compared against my input. What if we looked at which transistors were switching when that password was being accessed? It would tell me where that password is in memory. So essentially, I can follow the pattern of switching after I enter a password. Again, for this paper, it's not passwords on Windows. It's submitting a query for an AES encryption, but it's the same concept. I look for where the switching occurs, which circuitry lights up. I follow that back to where in memory things are fetched from. I take a strong laser and I just laze the crap out of it and make the data whatever I want it to be. So if I want to turn a 1 to a 0 or a 0 to a 1, I can use specific energy pulses that either relax or I don't know how much detail it's worth getting into, but you can switch the configuration of the logic bits in that location in memory to just make the key what you want, or read what the key is in the first place. So you can both extract secure information from this device or put your own information on it and put in whatever key you want and unlock it yourself, and basically render this encryption engine completely broken. And Xilinx was freaking out about this and sent like a cease and desist when we tried to publish this paper. It was kind of funny. Well, funny for me, not funny for them. But anyway, I think they worked it out. There's some interesting, I can talk more about how to reduce the likelihood of someone performing this attack, but there's enough material if you're interested. I can go into that as well. But that's one of the ways that infrared can be used to both take pictures, to break the encryption schemes that are on these devices. And I haven't talked about, like I said, I haven't talked about how to fix encryption schemes using infrared, but that's something I can talk about if you're interested. So this is probably the most familiar to everyone. Visible light spectrum is just taking a regular camera and taking a picture of a PCB like you see here. This board, the green one that's on the left, is a controller for a hard drive, a hard disk drive. And you can see several chips that are there. And we have several ways of taking pictures. One of them is a Nikon DSLR camera, and the one that you see on the right here is a Leica DVM something, or yeah, DVM6 microscope that can do several hundred times zoom. And the idea is finding out as much as I possibly can about this device. And there are many, many projects that we have that are working on this. You can talk to me and I will spend way too much of your time talking back to you about how, about these kind of projects and what we can do. But here are a few of them. So you can use properties of color palettes to do image normalization. So if you have 4 different people taking pictures with different cameras in different environments, and you want to compare them to each other and see what's different without actually getting noise from the environment, you can do many kinds of normalization from that. The other thing that you can do is look for shadows which indicate which components are tall and which components aren't, and use that for further filtering. Projects that I've done since making this slide is being able to figure out, based on looking at this image very closely, where the pins are, whether they're crooked or not, whether the number of pins matches the serial number from the package. So I don't know if I can zoom in on this one easily. See if this breaks everything. All right, it's not wanting to do that very easily. But anyway, if you look at the package right here, you can see a serial number that's printed on that device. And if you Google that serial number, oftentimes you'll see a data sheet that goes with it. That data sheet will tell you how many pins are on the device and the spacing of everything. And so if you have a calibration that tells you how many pixels are relative to this real world scale size, you can use that to figure out how closely this device matches what it claims to be. And that's a really powerful tool if you have people just remarking devices and selling them as a higher spec equivalent, even though it's just a garbage piece that they recycled from some dead board somewhere. So there's lots that we can do using visible light, but some of the more interesting ones come from X-ray. So this is way at the other end of the spectrum, where you use much more powerful and potentially dangerous equipment to take pictures as well. So the way that this is set up, you have a panel over here that looks for X-rays. You have a source over here that shoots out X-rays, and you have a sample. So if I took the same PCB from before, I would mount it on a pole that's right here in the middle between them. And that object would rotate. I'll see if this graphic works. There we go. I don't know how well that shows, but hopefully you can see. So the sample will be rotating like this while the X-ray is shooting beams and while the flat panel is recording them. And you get pictures that look like this. So as the device rotates at a head-on view, you'll see the full PCB. At a 45-degree tilt, you'll get something like this, so on and so forth. But you can use that to reconstruct a full 3D volume of the printed circuit board. And from there, you can do tons of interesting things. So here's just a quick project overview of being able to take that 3D volume that we've gotten, align it so that it's oriented relative to any sort of CAD schematics we might want to extract, do some sort of annotation of different properties for machine learning purposes, use those to get so if you're familiar with CAD, you might understand what DXF files are, Gerber files, drill files, all sorts of design schematics that you might make in KiCad, Eagle, Cadence, whatever software you want to design a PCB. But you can kind of back solve what those are from this X-ray volume if you use a bunch of tips and tricks and schemes that machine learning can provide you if you have enough annotated data. So these are some pretty cool projects that we're actively working on, collaborating with several different universities, several different kinds of X-rays, several kinds of boards, all of that stuff to do projects like this. And yeah, it's kind of interesting. If you, like, again, with any of these, if you have questions, I'm happy to talk to you way more about it. But that's very brief overview of the photonic imaging capabilities that we have. But obviously photons aren't the only way to take pictures. There are many others. And instead of receiving photons, what if we looked at electrons or ions or vibration of air particles or some other acoustic material? What if we looked at the magnetic momentum? Things like MRI imaging might do something like that, or positron emission tachography, or all of those things that you might hear about in medical imaging. Like we're starting to apply those to PCBs as well. And here is a bunch of different equipment that we have to do something like that. But the ones that I'll talk to you today about are the SemFib and NanoFab, because those are the ones that are at the Fix Lab, and you can literally walk into the lab and see those if you want. We did just put out a proposal that got accepted for a $300,000 scanning acoustic microscopy machine. So I'll add a slide for that after it's actually in the lab, but that one should be coming soon. So the way that this works at a very high level, you can, an analogy that might work is if you had someone standing against a brick wall and you were blindfolded and you had to find out where on the brick wall they were and kind of the general shape of that person. So say you're blindfolded, but you have a bunch of tennis balls in your hand. And if you throw them hard enough, if it hits the brick wall, it will, like, you'll maybe hear a small thunk and you'll see it bounce back, and maybe it'll bounce back to your feet, and you know, okay, it's a very reflective surface. I got the ball bounced all the way back to me, and I just heard a small thunk when it hit the wall. You throw it again and you hit the person on the wall, they might scream a little bit and the ball won't reflect back as far because they're soft. So you can look at how loud that person was and how far back the ball bounced to you. Even though you're not actually taking a picture of them, you can like keep on throwing it until you hear no more screams. Either they've died or you've got to the other side of them and you know that that's how wide they are, something like that. But you can get a good idea of where the wall is and where the person is. Not as interesting, but same concept. You can throw electrons at metal, and based on how quickly that metal, or based on the reflection characteristics of that of that electron and some of the damaging properties that it can do when it interacts with a device, you can use those to take really, really high resolution pictures of metallic objects, or conductive objects is the more correct term. And the only difference between scanning electron imaging and focused ion beam imaging is ions are much heavier than electrons. So instead of a tennis ball, if you threw a bowling ball, you can figure it would like crack the wall. It wouldn't just bounce right off. And so you can use things like focused ion beam imaging to mill away. So like actually etch away material on the metal that you're taking pictures of at the same time. And another phenomenon that happens if you threw a bowling ball so hard that the outer end of it got like liquid hot and it fused to the wall, you would actually add material to the wall. In that, again, this is an oversimplification, but the concept works. So in the same way, you can actually fuse ions to the material and do deposition as well. So milling and deposition are the two things you can do with ions as well. So what can you do with this? You can take really, really detailed pictures at the transistor level. So the image that you're looking at here, this is the scale bar at the bottom is 2 micrometers. And you can see P gate or P wells and N wells in the little bright spots that are here. You can see all of the different, if you've taken VLSI or anything like that, some of these structures might look familiar to you. It's the aspect of design down to the transistor level, and the so some of these things might look familiar. Otherwise, just think of this as like seeing the actual transistor level logic of what's going on something like a CPU die. So that's again the imaging portion. The deposition and delayering is people have used these to make very creative structures. So like here's a really, really, really small toilet that's on the scale of like 1 micrometer, I think. That this is not our lab. I think this is like MIT or somebody who was able to put this on a metallic structure with a deposition capabilities, and then you can see some very very finely calibrated features that are either milled or deposited with something like a focused ion beam on various objects. And something of note, this was done with the bottom right one was done with fixed lab equipment, and this is using the focused ion beam to mill away very, very precise amounts of silicon to depackage a die or like a chip's logic. And you can see if you mill away enough of a square of this, you can get a much better resolution picture of some of the transistor logic that's going on here. It allows you to do all sorts of nefarious things like make little wires between 2 different gates and change the logic structure of what's happening. Maybe make it tell you things about its secrets, all sorts of stuff. So that's one of the ways that this is relevant for how we use these equipment at Fixed Lab. So that's my whirlwind overview of some of the equipment that we have. How am I doing on time? Should I go quickly over this? Or? Okay. Okay, cool. Cool. Well, I'm not going to take that long, but we'll see. So if you're interested in grad school, I have a very brief PowerPoint that I made and attached to this one based on misconceptions from a lot of people in undergrad that I've talked to and misconceptions that I had when I was an undergrad. So first and foremost, these myths that I hear a lot. The first myth being that it costs money to attend graduate school. Maybe that's not as common at UF, like people here seem to understand that a little bit better. But if you're doing anthropology or history or a non-STEM degree, generally, yes, you do have to pay out of pocket. You have to pay a lot of money, and it's very hard to pay back because you don't make a lot of money after you graduate. And it is a very expensive endeavor, and you have to be passionate about what you're doing for it to be worth it. In engineering, that is absolutely not the case. So UF and the Florida Institute for Cybersecurity, where I work, the Fixed Lab in particular, pays pretty well as far as graduate degrees go. So I'm getting paid about $30,000 a year. It's not much, but I don't have to pay for tuition, and I get a stipend. It's enough to live off of to get my degree. So again, it's not a lot of money, especially compared to what you would make by going into industry. So I had an internship where I just made like $60 an hour without a degree working during my internship. So it's a little bit tearful to come back to my degree afterwards and continue working over the semester. But bottom line, it is free tuition. You do get stipend to live off of. So you're not taking out loans just to pay for rent. You get vacation days. A lot of those other things are the case. And if you're married, so I'm also married, fun fact, but and you can live off of your spouse's income, then it makes it a lot easier to make ends meet, especially in Gainesville with the lack of good housing and opportunities and everything. So, but all that to say, it is much cheaper than you might think if you talk to someone who's getting a history graduate degree. The other myth that I hear is like only really, really dedicated people go into grad school because it's so much harder than undergrad, and undergrad was a nightmare in and of itself. The reality that I have experienced and that most people I have talked to experience is if you like project-based work, it is significantly easier than undergrad. So as you can see in the bullet point there, most of the work is project-based. So you are responsible for your own objectives. You define how much you want to get out of your degree, and you work with your advisor to figure out what of that is feasible, how much, because they're still paying you to go to school, right? They want something out of it, but you have a lot of flexibility. It's a lot of project work, and it's more similar to a job than to a school. You do have to take classes, but only 1/3 of your credits are classes. The other 2/3 are just it's supervised research credits. That's all it is, and it's literally just writing papers, looking into things, reading articles. All of that stuff is mostly just independently motivated work, and you just coordinate with your advisor to see if they're happy with your progress, and if so, you're fine. So in that case, it is a lot easier than undergrad. I'm only it's 9 credits a semester instead of my undergrad was 18 credits a semester. I don't know what yours is like, but yeah, it's just so it's a lot more manageable. Generally, it fits within 20-25 hours a week. Really not that bad. And the other common thing is when people say, "Oh, if I was to do a grad program, I would be shoehorned into one thing for 5 years, and I would have no autonomy. I would just be doing this and not getting paid at all." Well, and the reality is at least some places that is true. There's an advisor with a specific research funding, and they say, we get funding for you to look at this project, and it will keep you funded for 5 years, but you have to look at exactly this. That happens. But something that you can ask about, and something that is also true of the Fixed Lab, which I can speak to in more detail because I have experience there. You can choose your own project. So when I came in, Dr. Asadi was asking me, what am I interested in? I said, I like x-rays. I like taking pictures. I like the idea of the physics behind imaging. And he's like, okay, great. Study that. And if you find something that you can write a paper on, cool, we'll do that. So it's just, I had a lot of freedom to choose my own projects. I got to choose the direction I wanted to go between balancing theory and practicality, and all of that other stuff. And it was kind of neat. And so like I would just reiterate one more time, many places you go in grad school, this is not a myth, it is fact. You have no creative freedom because you are paid to do a specific thing. However, especially true with the Fixed Lab, but also in many other places, if you negotiate that beforehand and just, again, coordinate with your advisor to have the right expectations, you can certainly have a lot more creative freedom in that regard. The other thing that people bring up is, again, why would you, even if you got paid to get a degree, why would you get paid $30,000 when you could get paid $110,000 to start with a bachelor's degree in hand? And I would hope to point you to this kind of chart where over US earnings, so this one is, I think, as of 2013, but new charts are still very comparable. The dotted line is income after there's several dotted lines. This chart is graphing the median annual income, as you can see, of people with master's versus bachelor's versus doctorate degrees. And all I want to point out is, yes, when you start with a bachelor's degree, having no experience and going into a job, you make more money, but the area under the curve is greatly in favor of after you get your degree, where a PhD gives you. So you just have, the ceiling is a lot higher in that regard. So again, in my personal experience, I had job offers for, I think the highest job offer I got after I got my undergrad degree was $100,000 roughly per year, which is still pretty good compared to a lot of places. After I am on my way out, I had an interview for a job that was $250,000 a year. So it's just very different. There are many options. And that is, again, it depends on who you know a lot. So I didn't just like walk into some office and slap down a resume and they were lining up for my phone number. I had to know people, but you have lots of opportunities to network for people who make decisions when you're in grad school. So these are people who I've been able to meet the CEO of the startup or whatever, see what their network looks like and build it and build that out. So I have a decent LinkedIn profile and it was able to I don't know, meet some of these people that actually can put you in those positions. So it's not just what the degree gives you, but the fact that you can network with interesting people who you would not normally meet, just kind of being a code monkey at a software engineering position in a large company somewhere. So that is something else to consider, not just the money itself. And then if you're interested in, okay, I'm in undergrad, maybe all of you are upperclassmen and it doesn't matter as much. But if you're wondering, okay, if I'm thinking about preparing myself for grad school and doing something with it, what can I do now to make that process easier? The only universal piece of advice I can give is it doesn't matter what you are doing. Everybody and their mother is doing machine learning nowadays. And if you look at the fundamental concepts of statistics, of probability, coding to some extent, popular frameworks like PyTorch and TensorFlow, you cannot go wrong. Literally everyone would be happy to have someone who has machine learning experience. I have not seen one single grad student out of the hundreds that I've interacted with that's not doing some level of machine learning, maybe like English and history, but in engineering, machine learning is everywhere and you would do well to prepare yourself if you're interested. I am doing a lot of image processing. So having classes like image processing and medical imaging helps you understand the physics and the computational characteristics of what this machine learning process does. So again, if you're not interested in medical or in image processing, if you're interested in like time series data or stock forecasting or whatever, the way that would translate to you is just knowing the physics of your data, because that is a lot easier to train a model on without bias than the circumstantial data that you get from data sets. So something like that is actually informative, depending on how much low-level research you're doing. And then, like I said, if you learn PyTorch, TensorFlow, things like that, those frameworks can get you very, very far, even if you're a little bit fuzzy on how machine learning concepts work. So things like programming classes, hobby projects, or whatever competitions, CTF is a great way of doing this. If it's, I know that there are some CTF that's more hardware-based, some that's more firmware, software-based. Any of that experience is very, very relevant. So it seems like you're a good crowd to already have that one under the belt. But yes, all of those will set you up very well above the average from what I've seen from. So I've had to interview several several undergrads looking for grad school at specifically the Fix Lab, and things like this are what sets apart people who can hit the ground running versus people who really struggle and at playing catch up for the first 2 years of their degree, which makes it a lot harder in my experience. So I think that is, I do have another slide that I added, which is mentality changes. And this is one that I only learned after like a year and a half, maybe 2 years of doing school, which is how to say no. In a lot of ways, in undergrad, you have a syllabus that's printed out at the beginning of the semester. You know how much work is required of you. You know what assignments there. You know how much each one contributes to your grade. Very cut and dry. I went into graduate school thinking, oh, I had a conversation with my advisor about what is expected of me. I can do these projects. I have a 4-year timeline to get my 90 credits, and then I'll be out of here, just like a syllabus, right? Wrong. If you finish your stuff early, you don't get a break. The advisor will basically tell you, great, you finish that, here's some more stuff that you can do. It's pretty much similar to a real world job. It's not like a rubric and a syllabus that you do and then you're done. It is a never ending slew of things that will never stop even after you're gone. And your responsibility is to learn where your boundaries are, where to say no, where to place the delineation between what you're working on and what is just too much of a commitment for the week. And that is okay. You get out of it what you put into it. So I did way too much. I have a decent number of publications as a result of it, but if I could do everything differently, I would have given myself more free time. And it's as easy as just balancing your workload and realizing it's not a syllabus. At least that's the key word that applied to me. And the other key one is finding a problem before you're looking for finding the problem before the solution. So in my experience with a lot of textbooks, especially math, they present the theory, how it's derived, what the proof is, and then they'll give you problems to demonstrate it. It is very rare for those kind of things to happen in grad school. Often you'll have this problem and a giant tool belt, but you'll have no idea what tools are relevant to solve the problem. And what can trip people up is they say, well, I've taken a machine learning course. Now, how can I apply that to every problem that I'm taking? And looking for the solution and trying to find problems that fit it is a lot less productive. In my experience, productive meaning it's harder to write papers about, it's harder to get good research direction. It's harder to ask your advisor for help when you say, here's what I know how to do. What can I do with it? Like that's a very open-ended question, and it's very difficult for them to advise you and to mentor you in that aspect. Whereas if you say, here's the problem I want to solve, they'll give you terms to Google, they'll give you resources. it's a lot easier to approach grad school that way. And again, it's just a mentality shift that helps to have when you're doing things like graduate school for an extended period of time and you don't want to burn out quickly. So again, something that I've learned after a little bit of doing it. And I think, yeah, that's the last slide that I have. And if there are any questions. Must have explained everything perfectly. Yeah, sure.
So when you're doing the infrared imaging of like some board or something, how do you practically do that while like sending memory to it? Like if it's
Great question. So if I go back to this slide, right here, no. Here. So I was trying to zoom in earlier and it wasn't letting me. Let me see if that's why it's in the web view. So I was zooming in on the web, but not actually. There we go. Do you see how there's a set of objective lenses over here? There's a camera in one of them. The board is actually plugged in here. So you can send inputs. There's an oscilloscope that's off the screen. So it's to the bottom right of this device right here that you can use as a function generator, as a measurement tool, as whatever. And so you can use that to feed inputs to the device. You can swap out between digital and infrared objective lenses, stuff like that, if that answers your question. And then to tune correctly the switching frequency. So remember, these bright spots are because you have tuned your model to take pictures at the same frequency as the device is running. So in the specific paper that generated this picture, they said, I know the device is operating at 3.2 gigahertz or something. I will make a query key that is 16 bits long. The first 8 bits are 1 and the second 8 bits are 0. So if I'm looking for that to be transmitted through memory, what is the switching frequency of a block of 1s followed by a block of 0? It's going to be half the device frequency, right? And if you know where your clock dividers are located and you look at which clock dividers from that device frequency, you know that the brightest one is going to be switching at 3.2 gigahertz. And then as you go down the clock dividers, you get lower and lower frequencies. So you can match which one is connected to which wires with the payload that you've sent to the device using this oscilloscope, and use that to tune how quickly you take pictures and hone in exactly on where you need to look on this device to find where memory is stored. And that's what was happening here. And yeah, so if I zoom in here again, the way that this paper worked, once they did that tuning, they saw, this block in memory and this block in memory are responsible for the encryption process. This over here is general purpose memory, and all of it would have looked the same if you didn't ask it for a secure payload and look where it was trying to find that payload in memory, essentially.
So you mentioned something about like extracting like AES keys from memory or something like that. Would you have to like, take like someone's computer or something or some device and then take it apart and put it in that machine and that kind of thing, and then you'd be able to do it?
That's one way of doing it. And it's less practical to talk about for a computer than for an FPGA. Or so the device that this was, you can see it's a Xilinx Kintex FPGA unit. Literally, you can see the text on here because it's a flip chip mounted, so you can actually image through it. And for that, yes, you would take the device, put it under a really strong laser, blast laser pulses against that device, and change the configuration of memory. However, there are other attacks. If you look, so Rowhammer is something you can look up. It's where you send, if you download someone's malicious code on your computer and it queries a line of cache billions of times, like per second, to the extent where you're rate limited by how quickly your memory can fetch and retrieve one row of memory, it has a like a capacitive coupling to the next line in memory. So essentially what you can do is trying to figure out how much to simplify this. The program that you've downloaded on your computer that shouldn't be able to access secure memory, if your computer happens to partition processes where it is adjacent to space and memory to a sensitive process, you can hammer, that's why it's called Rowhammer. You hammer a row of memory billions of times until you get capacitive coupling with the row above it, and you can leak information from that. So like that's one way you can get information. That's a whole other topic. DDR1 through 3 RAM, I think, is susceptible. DDR4 is coming around to not being as susceptible to it. But anyway, yes, for this specific purpose, you'd have to have someone with a laser over the actual location in memory of your device. I think this is SRAM blocks for it to work.
Oh,
Yeah.
So regarding this attack back to like the AES,
Yeah.
right? You said this was on a Xilinx FPGA.
Yeah.
How small of a scale can you get that to work on? Like, is this the kind of thing that you could do to a like modern ARM board?
Yeah, this is a modern device. I think it was like 2018.
Really?
Something like that.
Like this is you could do on like an iPhone.
So that I don't want to extrapolate more than I should. So the easy answer is I don't know. The more complicated answer is I think that even so marketing terms like transistor technology of 3 nanometers, 2 nanometers, that's mostly a marketing term. It doesn't mean that your transistors are 3 nanometers apart. It just means that your like gate width at the lowest width of the transistor device is 3 nanometers. But in reality, the spacing between transistors is still very large. So if you think of your transistor as this large and your spot size from your laser as this large, as long as the spot size is still like, you're not going to encounter multiple transistors in a row, you can still do the same thing that you're doing here.
Gotcha. I guess to rephrase my question, the latest chips that are coming out are at roughly the same scale where like this same thing works.
Yes, yes. So there are some caveats. Basically, if you have a really, really thick plastic packaging around your device, it's harder to see through it. You'd have to mill it down. That requires more equipment, it's harder to do. So to some extent, like an iPhone would have the same problems as this does. But yes, the roughly from 2018 to 2019, I think, manufacturing technology, that's still possible. Yeah. Also, people don't design very secure stuff, and it takes people publishing things like this before they actually want to do something about it. So.
You mentioned earlier when it came to using infrared to help extract AES keys, that when you went to go publish the paper, you actually got a cease and desist, and they were scrambling to go and fix the issue.
Yeah.
I believe you touched upon, like, I believe you mentioned that there are ways to mitigate
Yes.
this.
Yes.
What exactly are they?
So one of the things you can do is implant a noise generator in your circuit. So it just has random switching frequencies that are injected into all pipelines. So whether you're doing secure operations or insecure operations, it just injects random transistor bit flips in random places, and you know to ignore them as the designer, but the attacker doesn't know which ones are relevant and which ones aren't. But then what the person who wrote this paper did is just attack where that noise generator feeds into the circuit, chop it off, and now it's not generating noise anymore. So how do you solve against that? Well, so it's a chicken and egg problem, right? For every counterattack, there's a counterattack that makes it irrelevant. So anyway, very interesting story to read through the timeline. Yeah.
So this program has a lot of like opportunities for like grad school and like just general cybersecurity research in general, you would say?
Yes, absolutely. So the stuff I've talked about is imaging, because that's what I've done a lot of. If you are into firmware, there's people that do formal verification. There's people that do microkernel analysis. There are people that do, if you're into manufacturing, there's like, you can look at crosstalk effects. If you've heard of like chip whisper, you can do stuff like that. If you are into so I guess formal verification is more like systems programming, that you can look at kernel security. There's people that do IoT analysis. There's federated device networks, stuff like that. There are, if you're into RF, I think that we have a professor that's doing RF. Now, if you're into blockchain, we do blockchain. Almost any aspect of this cybersecurity, hardware security, as long as it touches hardware, you're pretty likely to find someone who's doing it.
Back to the AES stuff again. I imagine the stuff that you just told us here is not exactly a secret. So like if you're someone who makes a hardware secure module or in the business of making something that is full of signing stuff or holding keys, what other types of mitigations other than that?
Fair question.
Would those companies use to prevent?
Yes. So when it comes down to something like this, you're not saying, can I make a device that's completely impenetrable? Because that's not possible. The better question, yes, exactly. The better question is, can I make a device cost prohibitive, either by time, resources, whatever, cost prohibitive to attack? And so the device that was used to get these pictures costs around several $1 million, or I think it's $1.1 million, not several million. There's only so many of them around the world. And the people who have them are either like universities who have to sign some agreement or whatever, or nation states who have money to burn. And if you want to mass manufacture these chips, there's no way that you can prevent a single one of them from being held captive by a nation state and attacked like this. So instead, what you focus on is, can I keep it from being intercepted, modified, and retransmitted? And that's a lot easier to answer. So again, the trick is just to look at the threat model more closely and say, not necessarily how can I mitigate any form of these attacks, but how can I keep the threat models that I care about most from occurring? And so the noise generator one is that I talked about, like they proposed that one. It got kind of laughed at a little bit for that reason. You have to hook the noise generator in somewhere. Someone can look for noise that's not correlated to any chip activity. They can find out what is the strongest source of that noise, look for where that hooks into the rest of the circuit. There's only going to be one or two wires, cut them, problem solved. The other way of doing this is, so MEMS logic is getting a lot of attention nowadays, micro electromechanical systems. So it's where you use actual like topological structures. So not just wires for circuits, but heterogeneous packaging and some other fancy traits to, I don't know, probably more detail than it's worth getting into, but you can use stuff like that to mask, make it harder to figure out where to take pictures in the circuit. And another thing that people do is embed some sort of mesh. Like if you really, really want to produce expensive, but very like secure devices, you add like a really tiny mesh to the entire outside of the device, where if you pulse it with energy, then the mesh will say, I have a conductive current across me. Cut everything, zero every data on the chip, and no one can measure what's happening. So that's very expensive to make, but it's secure until you have someone who says, what if I embed two lasers that are going across each other like this, and no one laser triggers the conductive mesh, but where they meet in the middle, if I'm careful enough, I can still penetrate this security layer. So anyway, it's just, it is what it is. The stuff that probably is employed is the one that's not in papers right now, because either that or they're just crossing their fingers hoping someone doesn't actually use this, because yeah, I don't know.
Do you have any like must read or like favorite papers? I mean, this is super cool, but I don't have one of these machines in my bedroom, so I can't.
Sure. And that's why they haven't fixed as many of these things, because for that exact reason, you know. There's a couple of resources. So depending on which aspect of this you're interested in, I could recommend different papers. The one that this came from, I don't know why it's not on here. So shucks. I have a different slide deck that has the actual paper this came from. It's a survey of LFI, so laser fault injection is a term you can Google. If you look up Tanjiro Raman, who's the student from PIX who recently graduated, wrote this paper, came with a survey of why laser fault injection techniques matter. That would answer a lot of your questions about this specifically. Right? Yeah.
So this talk of like imaging security functionality on chips, it has me thinking of like trusted platform module
Yes.
chips and like, you know, the advent of Windows 11 and whatnot.
Yeah.
Does this come up at all in your current research or?
My current research, no. Colleague research very frequently.
Yeah.
And so one of the big things to note is if I scroll back up here to this motivational slide, why am I talking about Xbox 360s and not Xbox Ones or even Xbox One S or any of the modern stuff? Because they haven't been hacked. So
Right.
Microsoft saw this problem. It was prolific in the mod chip era, and they solved it. The trusted platform module is actually a so far unbroken way of making this work. And so yes, there are. So the question becomes, how do you communicate with peripherals? How do you know that the data that you're getting into your trusted platform module is secure? How do you know that you are not leaking information about how you are cryptographically securing this data during the computation? So like, am I emitting infrared in this thing? How do you know? Like, so all of those are follow-up questions that we can interrogate this TPM about. But yes, it is. It's very relevant, especially in the case of mod chips. Like it works. Solve the problem. Cryptography, it does wonders.
Yeah, going back to Cole's question, so do TPM chips incorporate any of these mitigations that you just mentioned?
I don't know. I'm not. So they could. I'm not the person to ask.
Gotcha.
Yeah.
So what you're saying is that if I want to play pirated games on my Xbox One, I need a like several $1 million machinery to get the keys from the trusted platform module.
Even then, so if the machine is smart enough and it's doing a sync, so your Xbox is probably connected to the internet. What could happen is if you trigger some sort of alarm or whatever on your system, the Xbox can refresh which keys are valid and which are not. The Xbox could tell central Microsoft server, hey, this key has been invalidated, and shut down your device. So that is another common way of mitigating these kind of attacks, is if you knew which keys were compromised, just invalidate the device or invalidate the data going across it. And yeah, something like that. So the other way that you can do this is make sure that the device only works with keys that have specific properties to them. And if you change that key, those properties are violated, and it also doesn't work. So like there's many things you could do.
Have you seen the Xbox One talk by Tony Chen with Microsoft? Well, it's in that case, like the keys are generated, the control flow path as it starts up that generates the keys that are used. So if you try to boot into the dev mode, it has a different key and you can't connect that up.
That's really interesting.
If you Google it, it's an awesome thought, but I also have a question.
Sure. Yeah, so just on that note, real quick, there's also a good talk on the PS3 security mechanisms and how it absolutely obliterated that came out several years ago, and it was because they did security at the OS level. So they all you have to do is just not boot into the OS, and everything is just there for the base. But yeah.
So we talk about this AES stuff again. When you explain it on slides, like it's easy to kind of conceptualize in your head. It sounds like you're watching a play-by-play, frame-by-frame of what's happening. In practice, and even take AES out of it, you just want to flip one bit to take a different branch. Like, that sounds when a modern CPU runs so quickly to flip that at the right time sounds impossible to me. Like, is that something you can actually do in practice, or do you have to?
Yeah, so it's only flipping quickly if the data across it is changing. So all you have to do is just not change the data. So one of the ways of doing that, if you have I said 16-bit before, I think if you have 64-bit addresses, if you make all 64 of those bits 1, and then the second payload is all 1s again, and then you wait until the 5th payload to go across 0s, you can still find where things are switching. You can also, so a lot of this has to do with periodic interactions. So if you laze at a specific frequency, you can only affect certain things. Often this laser fault injection stuff is more about attacking memory than attacking switches that are currently switching, because of that thing. Like if they're switching hard enough or fast enough, you can't deterministically make the fault in the same place in the same way every time. With memory, it is, even though the chip is running at 3.2 gigahertz, the data is not changing at memory at that speed. And so it's a lot easier to corrupt. Also, if the chip is off, you can do that. There's also a whole other mode. So I've talked about passive LFI right now, where you're reading data from the chip using this infrared sensor. There's active LFI, where you laze the machine and see where that pulse distributes throughout the circuit to see which things are connected elsewhere. It's another thing you could do that allows you to change the circuitry characteristics at low frequencies, because it's off and you get to control the frequency by pulsing it a certain way. If that answers the question.
I have my follow-up, but I'm gonna wait till after, so I don't take it the rest of the time.
Sure. Good questions.
One last question, I guess.
Yeah, sure.
Is there any what's the coolest other project that's going on right now at the Fix Lab in your opinion?
Cool is going to depend on what you're doing. So the cool to me,
Yeah,
I am now into generative models for machine learning. So the idea of, can you find defects in a circuit board without a data set of defects? By finding out what a statistical distribution of real components looks like and saying, what doesn't look like that? And if you think about it, that's kind of the way that we train humans. If I told you to find pictures of broken computer, or tell me when a computer is broken, I don't say, here are all the ways a computer breaks. I say, here's what a computer normally does. If it doesn't do that, talk to me and we can fix it. And it's a way of training machine learning networks to do the same thing. And it's kind of cool. Yeah.
Thanks so much.
Yeah, no problem.
Appreciate it. Perfect.
Let's